Hello everyone, I am Mujibur Khan. Today I'm going to talk about TDR moisture sensors and its use in precision monitoring for soil and water management. Precise soil moisture management is crucial for agriculture, construction, and environmental management. Traditional methods are often inaccurate and time consuming. In 1980, Canadian soil scientist Dr. Clark Top revolutionized this field with time domain reflectometry. He is considered the father of applying the technology of electromagnetic waves to the soil research. Let's explore how TDR sensors work and why they are essential for precision soil and water management. What is TDR? So TDR is a time domain reflectometry which uses electromagnetic waves to measure soil moisture instantly and accurately without disturbing the soil. Here in this figure we can see the TDR probes are inserted into soil and give the accurate result of how much volumetric water content is present in that area. So let's explore more how these things works. So TDR works in three basic steps, which includes sending an electric pulse. The TDR sensors have metal probes. Here you can see in the figure that send high frequency electromagnetic waves into the soil. And the second step is interaction with soil moisture. The pulse slows down when it encounters the water in the soil due to water's high dielectric permittivity. In the step 3, the reflection and measurement, the sensor measures the pulse's return time to determine the soil moisture content. To give a clear idea, we can see in this figure how these things actually work in details. So in TDR setup, as shown in the figure, the pulse generator sends an electromagnetic voltage plus pulse through the coaxial cable to the TDR probe. The TDR probe is inserted in the soil. The probe consists of stainless steel rods, and the pulse travels along these rods into the surrounding soil. As the pulse encounters changes in the soil properties, the part of the signals is reflected back. So the first reflection occurs when the pulse reaches the interface between the probe and the soil, while the second reflection happens at the open end of the probe. This reflection causes variation in the TDR waveform, and by measuring the time difference between the first and second reflections, the travel time of the signal is determined. This time is then used to calculate the soil's dielectric permittivity, which represents the soil's ability to store electrical energy. Then by using the Topps equation, which, which relates the dielectric permittivity to the soil moisture, the volumetric water content of the soil can be determined. The Topps equation converts the pulse reflection time into precise soil moisture percentages. Now, the modern TDR sensors still use this Topps equation for measuring the volumetric water content. In the figure, we can see the relation between bulk dielectric constant and the volumetric water content, which is this relationship is the basic of measuring the volumetric water content through TDR. Now let's go to the application of TDR in precision management. So TDR is widely used for soil moisture measurement. For accurate soil moisture measurement, it provides precise and reliable data on volumetric water content, which is essential for agriculture and environmental monitoring. It's a non-destructive technique, which allows for repeated, undistributed measurements and preserving soil integrity during analysis. It increases agricultural efficiency, optimizes irrigation systems by accurately determining the soil moisture, leading to a water conservation and improved crop yields. It's a real-time monitoring which enables Continuous real-time soil moisture data, crucial for irrigation scheduling and water resource management. For soil hydrological studies, it helps for understanding water movement, infiltration, and drainage patterns within the soils, and also important for hydrological and environmental research. So thank you everyone for your patience hearing.